10.6. Calculation of moments of inertia. The outline of this video is as follows. We will begin by working through an example involving a wheel and a hanging object to see rotational dynamics in action. Next, we will formalize the concept of moment of inertia for continuous, solid objects. We will then apply this formalism to calculate the moment of inertia for two common shapes: a uniform rigid rod and a uniform solid cylinder. Finally, we will introduce a powerful shortcut called the parallel axis theorem, which simplifies calculations for objects rotating about an axis that does not pass through their center of mass. Let us analyze a classic problem that combines translational and rotational dynamics: a mass hanging from a cord wrapped around a wheel. To solve this, we will break the system into two parts and apply the appropriate analysis model to each one. The hanging object is treated as a particle experiencing a net force, so its vertical motion is described by Newton's second law, F equals m times a. The wheel is a rigid object that rotates, so its motion is described by the rotational equivalent of Newton's law, where net torque equals the moment of inertia times the angular acceleration. This approach allows us to write separate equations for the object's translation and the wheel's rotation. The key insight is that the non-slipping cord constrains the system, creating a direct relationship between the object's linear acceleration and the wheel's angular acceleration. Now we will apply our analysis models to write the equations of motion for both the wheel and the hanging object. This is the analyze step of our problem-solving framework. First, let us look at the wheel, which is a rigid object under a net torque. The tension T from the cord is the only force that creates a torque, acting at a radius ARE. So the net torque is T times R, which from Newton's second law for rotation must equal I times alpha. This gives us our first equations. Next, we analyze the hanging mass, which is a particle under a net force. We have defined the downward direction as positive. The forces on the mass are gravity, m times g, pulling down, and tension, T, pulling up. So the net force is mg minus T, which equals m times a. This is our second equation. We now have two equations but three unknowns: a, alpha, and T. The final piece is the physical constraint that connects them. Because the cord does not slip, the linear acceleration of the mass, a, is related to the angular acceleration of the wheel, alpha, by the equation a equals r times alpha. With these three equations, we have a complete system that fully describes the motion. We now have a system of two equations with three unknowns: the acceleration, a, the angular acceleration, alpha, and the tension, T. The key to solving this is the physical constraint that the cord does not slip on the wheel. This no-slip condition provides our third equation, which relates the two types of acceleration, a equals r times alpha. We can use this relationship to combine our original force and torque equations into the single expression shown in line 3. A good strategy is to first solve this combined equation for the tension, T, which results in equation 4. With an expression for tension, we can substitute it back into the force equation for the mass. After simplifying the algebra, we arrive at equation 5, our final result for the translational acceleration. Notice that the denominator is greater than 1, which means the acceleration, a, will be less than g, the acceleration due to gravity. A powerful way to check our physics equations is to test them in an extreme or limiting case. Here, we will explore what happens if the wheel becomes infinitely massive, meaning its moment of inertia, I, approaches infinity. Conceptually, we would expect the small hanging object to be unable to rotate such a massive wheel. The system should remain at rest. Let us see if our math agrees. First, consider the acceleration. The equation is A equals g divided by the quantity 1 plus the fraction I over mr squared. As I becomes infinitely large, the denominator of the entire expression also becomes infinite. This causes the acceleration a to go to 0. Next, let us look at the tension. The equation is T equals mg divided by the quantity 1 plus the fraction mr squared over I. As I approaches infinity, the fraction mr squared over I goes to 0. This leaves us with T equals mg divided by 1, which is simply mg. The mathematical results confirm our physical intuition. With zero acceleration and a tension that perfectly balances the object's weight, the object hangs in equilibrium. So far, we have calculated the moment of inertia for a collection of separate point masses. We now extend this concept to solid, continuous objects, which is essential for analyzing most real-world rotating bodies. The core idea is to treat a solid object as if it were composed of an infinite number of tiny mass elements. We begin with our discrete formula, where I equals the sum of each mass element, delta m sub I, multiplied by its distance from the axis squared, r sub I squared. To handle a continuous body, we imagine these mass elements becoming infinitesimally small. In the language of calculus, we take the limit as delta m sub I approaches 0. This process of summing an infinite number of tiny pieces is precisely what an integral does. Our summation becomes an integral, giving us the general definition for the moment of inertia. I equals the integral of r squared dm. In this formula, dm represents an infinitesimal element of mass, and r is its perpendicular distance from the axis of rotations. To find the moment of inertia for a solid object, we integrate the quantity r squared dm over the object's entire volume. To calculate the moment of inertia, we need a practical way to handle the mass element, dim, inside the integral. The most effective strategy is to express this mass element in terms of spatial coordinates, using the object's density. For a general three-dimensional object, we use the volumetric mass density, written as the Greek letter ρ, which is mass per unit volume. This allows us to replace dm with the quantity ρ times dv, where dv is a small volume element. Our integral for the moment of inertia, I, then becomes the integral of ρ times r squared times dv. For objects with simpler geometries, we can use more convenient forms of density. For a flat, two-dimensional object like a metal plate, we use the surface mass density, sigma, defined as mass per unit area. For a thin, one-dimensional object like a rod, we use the linear mass density, lambda, which is mass per unit lengths. The key idea is that choosing the right density allows us to set up an integral over spatial dimensions like length, area, or volume, which is much easier to solve. Let us work through our first example of calculating the moment of inertia for a continuous object, a thin, uniform rod. This calculation demonstrates the general strategy of using integration to sum up the contributions from all the tiny mass elements that make up an object. First, we need a way to relate a small piece of mass, which we call dm, to a small piece of length, dx. We use the concept of linear mass density, represented by the Greek letter lambda. For a uniform rod, lambda is simply the total mass m divided by the total length L. So, a mass element dm is equal to lambda times dx, or the quantity m over L times dx. Now we can set up the integral for the moment of inertia, which is the integral of r squared dm. Here, the distance r from the central axis is simply the position x along the rod. We substitute our expression for dm, and since the axis is at the center, we integrate from x equals negative L over 2 to x equals positive L over 2. After performing the integration and evaluating at the limits, we arrive at the final result. The moment of inertia for a uniform rod rotating about its center of mass is 1/12 times the mass m times the length L squared. Let us now calculate the moment of inertia for a uniform solid cylinder, a very common shape in physics problems. Our strategy is to mentally divide the cylinder into a series of thin, nested cylindrical shells, each with a radius r and a very small thickness dr. First, we find the mass of one of these shells, which we call dm. The volume of a she will is its surface area, which is 2 pi r times the length L, multiplied by its thickness dr. The mass dm is simply the material's density, ρ, times this volume element. Next, we set up the integral for the moment of inertia, I sub z, which is the integral of r squared dm. We substitute our expression for dm and integrate with respect to the radius r, from the center where r is 0, out to the edge where r equals the total radius are. Finally, we substitute the definition of density, which is the total mass m, over the total volume pi r squared L. This leads to our final, important result. The moment of inertia of a solid cylinder about its central axis is 1/2 mr squared. Let us explore an important implication of the result we just derived for the solid cylinder. What would happen if we were to increase the cylinder's length while keeping its total mass m and its radius r exactly the same? This would simply make the cylinder less dense. If we look at our final expression for the moment of inertia about the central axis, we see that I equals 1/2 times the mass times the radius squared. Notice that the length, L, does not appear anywhere in this equation. This means that the moment of inertia of the cylinder around its central axis is completely independent of its lengths. Therefore, stretching the mass along the axis of rotation does not change how difficult it is to spin. This formula works just as well for a long, thin cylinder as it does for a short, flat disk, as long as they share the same mass and radius. For rotation about this axis, only the radial distribution of mass matters. Calculating the moment of inertia for an axis that does not pass through an object's center of mass can be mathematically intensive. Fortunately, the parallel axis theorem provides a powerful shortcut for this exact scenario, as long as the new axis is parallel to an axis through the center of mass. The theorem states that the moment of inertia, I, about any axis, is the sum of two quantities. The first is the moment of inertia about the parallel axis through the center of mass, which we label as I sub cm. To this, we add a second term, the total mass of the object, m, multiplied by the square of the perpendicular distance, d, between the two axes. This gives us the concise formula. I equals I sub cm plus m times d squared. For example, if you know the moment of inertia of a rod about its center, you can use this theorem to easily find it about one of its ends. This relationship also reveals that an object's moment of inertia is always smallest about an axis passing through its center of mass. Let us apply the parallel axis theorem to find the moment of inertia of a uniform rigid rod about an axis through one of its ends. This is a classic example that demonstrates the power of this theorem for simplifying what would otherwise be a more complex integration problem. We start with two key pieces of information. First, we recall the moment of inertia about the rod's center of mass, ICM, which is 1/12 times the mass m times the length L squared. Second, we identify the distance, d, between the center of mass axis and our new axis at the end. For a uniform rod of length L, this distance is simply L divided by 2. Now, we substitute these values into the parallel axis theorem, which is I equals ICM plus m times d squared. This gives us the expression 1/12 ml squared plus m times the quantity L over 2 squared. Squaring the L over 2 term gives us 1/4 ml squared. Adding the two terms together, 1/12 plus 1/4 results in 4/12, which simplifies to 1/3. The moment of inertia for a uniform rod rotating about its end is 1/3 ml squared. Let us summarize the key tools for analyzing rigid body rotation. Our primary strategy is to combine the laws for translational and rotational motion. We use the familiar net force equals m times a for translation, and its rotational equivalent, net torque, equals I times alpha. We then link these two descriptions with a constraint equation, like the no-slip condition where acceleration a equals r times alpha for a rolling object. The moment of inertia, I, measures how mass is distributed around the rotation axis. For any continuous object, we can always find it using the fundamental definition, where I is the integral of r squared dm over the entire body. Finally, the parallel axis theorem gives us a practical shortcut. It allows us to find the moment of inertia about any axis by starting with the moment of inertia through the center of mass and adding the term m times d squared, where d is the distance between the axes. These principles provide a complete framework for analyzing rotational dynamics. To wrap up, here are two review questions that apply the principles we have just discussed. The first question asks you to modify the pulley problem from our earlier example. Imagine that the mass is being pulled upwards, causing it to accelerate in the upward direction. The key to solving this is to revisit Newton's second law for the hanging mass. If we take the upward direction as positive, the net force equation becomes T minus m times g equals m times a. Using this new equation, you can work through the derivation again to find the modified expression for acceleration. The second question is a direct application of the parallel axis theorem. You are given the moment of inertia of a square plate about its center of mass, and you need to find it about an axis through a corner. Remember the formula. I equals ICM plus m times d squared. Your main task is to calculate the distance d from the center of the square to one of its corners, which you can find using the Pythagorean theorems. These problems are great practice, so I encourage you to pause here and work through the solutions on your own.